This is Mars. We've always dreamed of going there, haven't we? Imagining humanity living under that alien red sky. But maybe we're ignoring a harsh truth. Mars isn't like Earth. It's incredibly hostile. Freezing temperatures, deadly radiation, and not a single breath of air we can use. So the real question is, can humans actually survive on Mars? Or is it just a risky dream we're not ready to face? I am Jay, and you're watching Astrosium. Let's get to our topic. For generations, Mars served as a canvas for our hopes and fears. Today, the ambition of becoming a multi-planetary species confronts the stark reality of the red planet. And that reality is sobering. Mars is fundamentally alien to earthly life. It is a frozen desert world, constantly exposed to dangerous levels of space radiation due to its lack of a global magnetic field and substantial atmosphere. The air is a near vacuum, completely unbreathable. Temperatures fluctuate dramatically, plummeting to levels far colder than Antarctica. Survival itself demands immense technological support and challenges the limits of human endurance. It is a world inherently hostile to complex life. Establishing even a basic foothold would require extraordinary technological effort and human resilience simply to exist. Given such profound challenges, the question must be asked, why? Why contemplate investing potentially trillions of dollars and vast human effort into this desolate world? The justifications often cited are significant, ensuring humanity's long-term survival by establishing a presence beyond Earth, a hedge against terrestrial catastrophe. The pursuit of scientific knowledge, unlocking secrets about planet formation and the potential for past Martian life, and the drive for innovation that pushes technological frontiers. However, these motivations face serious counterarguments. Is Mars the most practical lifeboat? Consider Antarctica. Here on our own planet, with breathable air, accessible water, and far less radiation, we have only managed to establish small, specialized research stations, not large, self-sufficient settlements. The difficulties on Mars are orders of magnitude greater. Many argue, with considerable weight, that the immense resources required for even a minimal Mars presence could be more effectively allocated to addressing the urgent existential challenges we face on our proven, life-sustaining home planet. The debate is complex, extending beyond science and engineering into economics, ethics, and our fundamental priorities as a species. Is Mars an essential next step, or a potentially dangerous and costly diversion from critical terrestrial needs? Sending humans to Mars isn't just about building rockets or planting flags. It's about confronting a hostile world with no air to breathe, no protection from the cosmos, and no room for error. Before we can talk about building homes on the red planet, we must first overcome its most unforgiving realities and challenges. Let's explore 6 major challenges we must overcome before we can even consider moving to Mars. For humans to survive on Mars, the first fundamental obstacle is the air. Mars offers nothing suitable for breathing. For decades, the prevailing concept involved transporting heavy, bulky oxygen tanks from Earth, a logistical nightmare for any mission beyond a brief visit. A significant step forward came with MOXIE. This experimental device aboard the Perseverance rover successfully generated a small quantity of oxygen from the Martian carbon dioxide atmosphere. It's a remarkable proof of concept, demonstrating that using local resources is possible. However, scaling this technology up presents a formidable challenge. Providing breathable air for even a modest permanent habitat, let alone a larger settlement, would necessitate industrial-scale chemical processing plants. These would demand enormous power supplies and require continuous, complex maintenance in a hazardous environment. MOXIE represents a crucial first step, but it has not solved the challenge of providing breathable air at the scale required for a settlement. Mars provides scant protection from the relentless bombardment of high-energy radiation originating from deep space and the Sun. Without a global magnetic field or a thick atmosphere, the surface is exposed to radiation levels far exceeding established safety limits for long-term human health, significantly increasing risks of cancer, cataracts, and potential neurological damage. How can inhabitants be adequately shielded? Transporting heavy shielding materials from Earth is largely impractical. Utilizing the Martian soil, or regolith, offers a potential solution, either by piling it thickly over structures or incorporating it into 3D printed building materials. Seeking refuge in natural underground lava tubes is another possibility. However, both approaches require substantial construction capabilities, likely involving complex robotics or human extravehicular activity in dangerous conditions. Advanced materials designed for lightweight radiation shielding are under development in laboratories, but they are far from ready for large-scale deployment in spacesuits and habitats. Furthermore, the long-term health effects of residing, even with shielding, under chronic Martian radiation levels remain a significant unknown. Before even considering the dangers of landing on Mars, just reaching the planet efficiently is a major challenge shaped by the laws of orbital mechanics. Earth and Mars travel around the Sun at different speeds and distances, which means you can't just launch a rocket toward Mars at any time. Instead, missions must take advantage of precise launch windows, rare moments when the planets align perfectly to allow for a fuel-efficient path. These windows only occur about once every 26 months. Missing one doesn't just cause delays, it can push a mission back by over 2 years, creating serious obstacles for mission planning, supply chains, and any hope of rapid emergency response for a future Mars outpost. For a deeper dive into orbital mechanics and launch windows, check out our other video here or check its link in description. You can watch that video after this one. Reaching Mars' orbit is one major challenge. Landing safely on the surface, especially with the massive payloads required for human missions, presents another level of difficulty. Earth's dense atmosphere provides substantial braking. Mars' thin atmosphere offers very little resistance to slow down multi-ton spacecraft arriving at hypersonic velocities. The landing systems successfully used for robotic explorers, such as parachutes and the sky crane mechanism, are inadequate for the scale required to deliver habitats, ascent vehicles, and supplies for human crews. This entry, descent, and landing problem for heavy payloads has long been a critical barrier. Promising technologies are now being tested, including large inflatable heat shields to maximize atmospheric drag and supersonic retropropulsion, firing powerful braking rockets while the vehicle is still traveling at supersonic speeds. However, these are complex systems still in development. Reliably landing structures weighing tens or even hundreds of tons on Mars, repeatedly and safely, remains a formidable engineering hurdle yet to be definitively solved. Once safely landed, long-term survival depends on accessing and utilizing local resources. While Mars appears desiccated, scientific evidence confirms the presence of water ice, frozen beneath the surface and locked within minerals. However, locating accessible deposits and then reliably extracting, melting, and purifying the vast quantities of water needed for drinking, sanitation, agriculture, and potentially rocket fuel production represents a monumental industrial undertaking, far more complex than drilling a terrestrial well. What about food production? Martian soil is toxic to Earth plants and lacks essential organic matter. Agriculture would necessitate large, pressurized, artificially lit facilities using hydroponic or aeroponic techniques. Essentially, complex food factories requiring continuous power, water, nutrient cycling, and maintenance. Power generation itself is a significant challenge. Solar panels are less efficient due to Mars' greater distance from the Sun and the pervasive dust. Compact nuclear reactors offer a potential solution for consistent power, but involve considerations of safety, maintenance, and shielding. Achieving even basic self-sufficiency for a small crew necessitates an intricate, fragile technological ecosystem. A failure in one critical system could have cascading, potentially catastrophic consequences. Scaling these systems to reliably support a large population remains beyond our current technological horizon. Even if the immense technological hurdles could be overcome, the human element remains profoundly challenging. Mars is unimaginably distant. Communication delays render real-time conversation impossible, stretching up to 40 minutes for a round trip. During periods of solar conjunction, when the Sun blocks the path between Earth and Mars, communication can be cut off entirely for weeks. Emergencies would have to be managed autonomously, without immediate guidance or support from Earth. The psychological burden of extreme isolation, confinement with a small group under constant pressure, perpetual danger, and irreversible separation from Earth's biosphere would be immense. Maintaining mental health, crew cohesion, and optimal performance over years, potentially entire lifetimes, presents challenges we are only beginning to comprehend. Furthermore, the long-term physiological effects of living under Martian gravity, approximately 38% of Earth's, on the human body, including bones, muscles, cardiovascular system, and sensory perception, are largely unknown. And perhaps the most fundamental biological question remains unanswered: human reproduction. Is it possible for humans to successfully conceive, carry a pregnancy to term, and give birth on Mars? Could children develop normally, both physically and neurologically, in the reduced gravity and higher radiation environment? We currently lack any data to answer these critical questions. Without the ability to reproduce and raise healthy subsequent generations, the vision of a truly self-sustaining Martian colony remains purely speculative. This biological uncertainty, coupled with the profound ethical considerations involved, may represent the ultimate barrier to long-term human settlement. Could humans live on Mars? For select, highly supported individuals, for limited periods, the answer is perhaps yes, albeit at enormous expense and considerable risk. But can we establish a permanent, self-sufficient human civilization on the Red Planet? The obstacles, technological, biological, psychological, societal, ethical, and economic, are staggering. We face difficulties sustaining human presence in the most extreme environments on our own planet. Mars presents challenges that are exponentially greater. The Red Planet may continue to beckon, but perhaps the greatest endeavor lies not in conquering Mars, but in safeguarding our own world. So what do you think? Should humanity do whatever it takes to reach Mars, or should we focus on fixing the problems here on Earth first? I'd love to hear your thoughts in the comments below. And if you enjoyed this video, consider subscribing to Astrosium for more deep dives into space and science.